Deep inside a standard Kerr black hole, stellar collapse culminates in a terminal singularity. A mass equivalent to millions of suns compresses into a zero-dimensional point, driving the density of that location to literal infinity. Einstein's general relativity maps the gravitational collapse of this star with absolute precision, right up until the matter reaches that exact center. At that coordinate, the equations stop producing physical answers. The mathematics output a divide by zero error, yielding infinite density and infinite curvature. A parallel crisis exists at the opposite end of the size spectrum. In quantum field theory, the framework we use to describe subatomic particle interactions, calculating the energy of certain particle exchanges produces infinite divergences. The math dictates that particles require infinite energy to interact, which contradicts the finite reality we observe. These infinities are not physical realities, they are mathematical artifacts. When a cosmic model predicts infinite density and a quantum model predicts infinite energy, the universe is not breaking down. The geometric model we are using to describe the universe is simply incomplete. To resolve this, we turn to the Einstein-Cartan-Sciama-Kibble, or ECSK theory. ECSK is an extension of general relativity that integrates the quantum mechanical properties of matter into the structure of the gravitational field. The critical modification ECSK makes is the introduction of a dynamic variable called torsion. Torsion is a twisting property embedded directly into the geometry of spacetime. Standard equations assume spacetime behaves like a flexible canvas that can only bend or curve under the weight of mass. ECSK theory argues that spacetime is more like a woven fabric that can both curve under mass and twist under localized forces. At the macroscopic scale, this twisting geometry prevents matter from compressing into a terminal singularity. Instead, the collapsing matter reaches a maximum finite density, halts, and rebounds in a big bounce that births an entirely new expanding universe. At the microscopic scale, applying this exact same torsional geometry to particle interactions automatically neutralizes the infinite energy divergences in quantum field theory. Torsion provides a single, unified mathematical engine. It connects the birth of cosmic structures directly to the stability of the subatomic world. Standard gravity relies on the Levi-Civita connection. This is a mathematical constraint dictating that the affine connection of spacetime is perfectly symmetrical. Under this rule, spacetime can only curve. This purely symmetrical assumption works perfectly for planets and stars, but it fails to account for the intrinsic properties of elementary particles at the quantum level. ECSK theory removes that symmetry constraint. It allows the affine connection to possess an anti-symmetric component, freeing the local geometry to twist independently of the macroscopic curve. The physical driver of this twisting motion is the intrinsic angular momentum, the spin of Dirac fermions. Dirac fermions are elementary particles, like electrons and quarks, that make up all physical matter. At standard astronomical densities, the torsional twist generated by these particles is entirely negligible. The curvature of gravity dictates the motion of planets, and we never feel the localized twisting of spacetime. The geometry undergoes a phase change when matter reaches an extreme density, specifically approaching 10 to the 46th power kilograms per cubic meter. In this environment, the spin-torsion coupling scales up and becomes the dominant geometric force. This extreme density state manifests as a massive, repulsive spin-spin interaction. The localized twisting of spacetime exerts an outward pressure that physically pushes fermionic matter apart. Because elementary particles possess spin, the geometry of the universe mathematically forbids matter from ever compressing into a zero-dimensional point. We can track exactly how this mechanism operates inside a dying star. As stellar mass exhausts its nuclear fuel, it collapses inward, crossing the event horizon and plummeting toward the center of the gravitational well. As the matter approaches the Planck scale, the density reaches that critical threshold. The repulsive torsion vectors generated by the spinning fermions finally overwhelm the attractive gravitational curvature. The collapse decelerates, halts entirely, and violently rebounds. This is the big bounce. The repulsive force of torsion permanently halts the inward trajectory, capping the star's collapse at a finite maximum density limit. The extreme gravitational energy concentrated during this bounce triggers intense quantum particle production. The vacuum itself begins producing massive quantities of new fermions. The immense addition of newly created mass and energy drives a finite period of exponential outward expansion. This rapid recoil mimics the exact conditions of cosmic inflation. The interior of the black hole has transitioned into a new, expanding universe, causally disconnected from the outside. The mathematics dictate that our own expanding cosmos, tracing back to the Big Bang, was a big bounce that occurred inside a parent universe's black hole. We can scale down from macroscopic cosmology to observe the exact same geometry operating on the quantum interactions within that newly forged matter. The core mathematical flaw in standard quantum field theory is its reliance on continuous integral loops. When calculating the self-energy of a particle, the continuous integration over all possible momenta stretches to infinity. This continuous looping is the direct cause of UV divergence. It produces the infinite energy errors that break the equations and require physicists to impose artificial mathematical cutoffs to get usable answers. Introducing torsional spacetime corrects this quantum framework automatically. In a twisting torsional spacetime, momentum components become non-commutative. Non-commutative means that the order in which you measure or multiply these spatial components changes the final result. This non-commutative geometry forces the continuous momentum space to break apart. It separates the space into discrete, quantized energy levels, where the distance between the levels increases as the energy scales up. Mathematically, this eliminates continuous integrals entirely. The continuous loops are replaced by discrete summations over specific eigenvalues. When physicists apply this torsional regularization to standard models, it successfully yields finite, calculable bare masses for the electron, the muon, and the tau lepton, without requiring any artificial cutoffs. Geometric torsion removes the infinities from our quantum equations. It proves that the universe regulates its own energy states at the subatomic scale, just as it regulates its density limit at the cosmic scale. If singularity-free black holes exist in reality, and not just on paper, we have to find a way to observe them in the sky. Observational astrophysics currently operates on the assumption that all uncharged rotating black holes are described by the Kerr metric. The Kerr solution explicitly contains a curvature singularity, which is exposed whenever its denominator reaches zero. We can contrast the Kerr metric with regular black hole metrics, such as the Bardeen or Hayward models. These regular models adapt the mathematics of the event horizon to completely erase the terminal singularity at the center. Regular metrics achieve this erasure by introducing a specific deformation parameter into the equations. Finding physical evidence of this deformation parameter in an actual black hole is the only empirical way to prove they act as cosmic conduits. Testing these competing metrics requires millimeter and submillimeter very long baseline interferometry, or VLBI. This technique links radio telescopes across the globe to create a single Earth-sized observational lens. This image of the M87 supermassive black hole, captured by the Event Horizon Telescope, serves as our baseline. It gives us a direct view of the immediate boundary, specifically the photon capture sphere, where light orbits the event horizon. To test the metric, astronomers measure the shadow's distortion parameter, checking the photon capture radius for deviations from a perfect circle. Spin naturally causes an asymmetrical dent. Because spacetime rotates, the capture radius differs for photons moving with the rotation versus those moving against it. For non-rotating black holes, this measurement is highly effective. The dent in the shadow cleanly and obviously differentiates singular Kerr metrics from singularity-free regular metrics. However, there is a fatal parameter degeneracy problem. For fast-spinning near-extremal black holes, like the ones we actually observe, the deformation parameters overlap. The shadow shape of a spinning Kerr metric and a spinning regular metric look nearly identical to our instruments. This geometric degeneracy forms a strict observational limit, preventing us from differentiating between a standard singularity and a torsional bounce in the real universe. Torsion offers an elegant, unified resolution to the crises of spacetime singularities and quantum divergences. But confirming that black holes are the reproductive engines of the cosmos remains trapped behind the blur of extreme spin observational degeneracy.